Hello and welcome to episode number 2 of the Web3 Odyssey. I'm Omer and I'm here with my co-founder Yehonatan Cohen-Scully. We'll be talking about the future of cryptography. Let's get started. So Yehonatan, I know that your background is starting when you were really young. Can you tell us a little bit about your background with cryptography?
Yeah, so that for me, cryptography actually starts with math, and math started for me very early. When I was 16, I started my first degree in math. I did it during high school, and from that, I finished at 19. From that, I went into the army to a special unit. It's called Matzov. It's the central unit for both cryptography and defensive cybersecurity. And actually, during Matzov, I wanted to do something a bit different. I wanted to kind of switch from the math side into the more like computer science, cybersecurity stuff. And it was very interesting, totally interesting. I did it for 5 years, and following that, I did some more offensive cybersecurity. But when I saw crypto, I saw this like huge challenge of protecting billions of assets in very challenging ways, because you actually have to defend against threats in scales like I used to defend in the army. And I saw that, and at first I thought it's going to be a cybersecurity solution because it's a cybersecurity problem. But as I started to learn more and more about how blockchains work, how cryptography is integrated into blockchains, what I understood is that cryptography is actually the top enabler and the top thing to focus on when you build a defensive solution for Web3. And this is what I've been doing for this time. I've been starting to go back into the roots, into math. And it was brilliant. It was so interesting for me to go back. I love it, and I kind of missed it. And cryptography is very interesting. It's like you take cybersecurity, but you formalize it into like equations that you can actually prove when something is going to work, or you can prove that it's broken.
That's really interesting, Yehonatan. So for our audience, I know that all of them are into crypto and Bitcoin and blockchains, but I'm sure that not all of them really knows exactly what is cryptography and how is it connected to math. So can you tell us a little bit about that?
Yeah, it's funny. Just today I talked with one of our cryptographer, and we raised this idea. And then he said, I can break it with pen and pencil, which actually he did, because that's something that you can do, and it's math. But how can you do that? How can you break an entire scheme with just a pen and pencil? Well, I think the answer is revolving around how cryptography is actually built, what's the building blocks of cryptography. And they're actually based upon mathematical problems. Mathematical problems that are considered computationally hard, right? One very famous cryptography problem is the discrete log problem, which basically means that you have some kind of value that if you knew the logarithm of that value, then you could have broken the entire cryptography scheme. But because you operate in very specific groups, mathematical constructions that just make it very, very computationally hard to actually make that, calculate that without actually knowing the answer from beforehand. And I think that these kind of problems is what cryptography is built upon. You take this like very simple problem, like taking a logarithm of some number, and then when you show that if this problem is hard, you use that problem in various ways in order to show that you actually can do something magical, like proving that you signed some data and only you knew what was possible in order to sign that data. And this is basically cryptography. It's that transition from very low-level mathematical problems into equations that you can prove or break with pencils, basically.
So what you're basically said is that the building blocks in cryptography are cryptographic problems, right? If I understood it correct.
Yeah, mathematical problems.
In your background, you have also cybersecurity. Can you tell us what is the connection and what are the differences between cryptography to cybersecurity?
Yeah, I'll do that, but it's a bit challenging because, well, cybersecurity is not very alike to cryptography in many ways. It's much more debatable. It's much more up for interpretation than cryptography. Cryptography, you can simply show that you have an assumption, that if that assumption it holds, then your entire scheme is completely protected and there's nothing you can do to break it. But then in cybersecurity, you need to prove, well, you cannot really prove that you don't have any bugs in your code, right? That no vulnerabilities exist or that you have completely sealed all the attack vectors. It's completely hard. And I think that although many people try to, wave their hands around and say like our product solves everything or this is secure, like what I've seen in my lifetime is that everything is breakable. I've worked with the most talented people in both defensive and offensive cybersecurity, and I've really seen pretty much that nothing is really secure. Like if you look at cybersecurity and you assume that this machine cannot be hacked or my phone is protected, or those assumptions almost never hold. And I think that this is a really big difference. And when we try to do something that revolves around cryptography, and there is the question that, okay, cryptography is one aspect, but cybersecurity will continue to be an aspect. Actually, once the entire intelligence community, they didn't care about cybersecurity. Like cybersecurity wasn't a thing. What was the thing was breaking cryptography. You had encryptions, you could intercept the communication, and you needed to break the cryptography. And after the computer science field of cryptography has advanced enough, it's no longer a thing. Like, yeah, cryptography can be broken still if you use it in a wrong way, but a lot of times, for example, if you look at the institutional world right now and you look about things like HTTP or SSL, they're actively spread all over. Most of the times you can't really break the cryptography, and what you need to do actually is to break the person that holds the key. And I think that's the transition that really happened is from trying to break cryptography schemes into just hacking an individual. And lately it has become also hard to hack into devices. For example, Android and iPhone have done pretty good job in making their operating system rather secure. When I say rather, it's like it just depends on who has the incentive into breaking into your phone, for example. But it still can be done. And I think that the real important kind of point that stretches both cryptography and cybersecurity is when you look down at the lowest level of the building blocks. In cryptography, you have the mathematical building blocks that you assume are perfect. In cybersecurity, you have the CPU, its instruction set, and from that you can understand exactly memory formation, how the operating system uses that CPU and program that CPU in order to distinguish, for example, between kernel space and user space. And these are the only kind of parallelism that I could have made. It's also the only thing that I could have actually relied upon when I try to do threat management. Is I know that if you have in the user manual of the Intel CPU, you have like instructions and they say exactly what they're gonna do, then you can assume that as long as this holds, and you build upon it in a correct way, then your solution may hold. But in the end, I think that lately, with the fall of many TEs like Intel SGX or AMD SEV, we have shown that even this lowest level in computer science of the instruction level guarantees, these assumptions are simply not strong enough, and they are repeatedly broken, and their threat model is repeatedly broken. And this is why when we think about how can we make a system that is provably secure, that is actually going to withstand threats that are on the level of billions of dollars of intelligence communities or of private hackers that have unlimited funds, then the only solution that I can think of must come from a proven cryptographical solution. And maybe in the future we'll have something that might support just that.
So I know that everybody knows that crypto is all based on cryptography, but most of the blockchains and the crypto that we know up to today is based on the old school cryptography. But we know that, and not everybody know that, but that a lot have been changed in the last few years in cryptography. So can you tell us a little bit about modern cryptography and how it's really going to change the crypto space?
Yeah, it's actually funny because so the cryptography in Bitcoin is completely standard. It's just digital signatures used for identification. But
this is not authentication, right?
Yeah, that's just authentication layer is completely standard. There's nothing interesting or new about it, nothing revolutionary whatsoever. But that choice has led into just a sequence of advances in modern cryptography in a way that is kind of funny to look at, because blockchains like Bitcoin and Ethereum are completely separated from the external world. They don't have any means of communications rather than a user broadcasts a transaction, queries a result. And as someone who's trying to build some kind of solution on top of these blockchains, you're faced with pretty much two options. You either build something that still requires trust in you, or you need to come up with this new way that you can actually prove that your addition is trustless. And the problem is that you really can't change the logic of Bitcoin and Ethereum in order to support your causes, right? If you look at something like Fireblocks, they are doing a wallet that allows you to separate different identities to control the same account in Bitcoin or Ethereum or whatever. And you would think something like, okay, but it would be much more useful if we could simply insert some new logic that would support it into the original blockchain, right? Why would we need to do it separately? But the real thing is that blockchains are built to be censorship resistant. They're built in a way that they want to be as simple as possible. The authentication should be as simple as possible. And this model of not your keys, not your coins, like it must be held at least in the level of the blockchain. And I think this is why this blockchain is chosen deliberately to simply allow any user that holds an account to do anything that he wants, because otherwise, where does the limit pass? And if someone wants to put some restrictions upon himself, whether it be for security or regulatory reasons, I don't know, then it would have to be external. And one of the cryptographer that I met, she just told me, what's the problem? Just when you check for the digital signature, also check for the condition. Why do you need to assure the condition before you generate the digital signature? And I told her, well, because I cannot change the original code of the one that verifies the digital signature. And I think this inflexibility of code, of the design of the blockchains, this, like, I see it like a stone that but you need to come at it from different directions in order to make it work without changing the original thing. And because they have chosen to support only this thing, only this small cryptographic primitive, then what it actually caused was everyone else needed to develop the most cutting edge cryptography in order to assure that their interaction with the blockchain is completely trustless and it's proven secure. And this has spawned like major advancement in fields like threshold signatures, zero knowledge proofs, and I think the future holds even further advancements, even on the theoretical level, not only about practicalities. But yeah, that's it. Like this small thing has caused complete changes in the entire world of cryptography. And I think that the reason is because there is too much money, and it's its raw state, it's just not sufficiently secure for real world usage. And so all of this money had to go into research to support and enable people to actually use this in the real world in a way that they feel secure about.
So let's talk about Odyssey and D-Wallet. Let's go deeper. We all know that Odyssey and D-Wallet, the whole idea is that it will be access control layer to Web3, to other blockchains. And what you're saying is that it's really, really hard because of the design, the old design of blockchains, like using ECDSA, right? Signatures, that you have to rely on them. My question is, in Odyssey, when you design the wallets, how you overcome this compatibility issue with the existing blockchains, because you can't really change their authentication mechanism, right? You have to rely on the existing one, but at the same time, you want to make sure that you create these new capabilities of being able to control the access to those blockchains. So what's the way to solve that with, my guess is with modern cryptography, right? But what exactly, how you do that?
Yeah, I think that was the point of my previous answer, is that you'd have to do it in a way that you still interact with the blockchain as a normal user. It doesn't experience any difference from the blockchain side. It doesn't know that there is this whole new blockchain that's called Odyssey, and it's the most magnificent blockchain ever created, and it holds this new concept called D-wallets, and everyone loves it. No, it doesn't care about that. Bitcoin, from Bitcoin's perspective, simply sees an account, which is a user account that broadcasts some digital signature, and it verifies that digital signature, which is independent of whether it's Bitcoin or not. It's just normal digital signature, and that's it. It just executes the transaction and changes the state. And that's our goal, to be transparent. It's our goal to be compatible in a way that Bitcoin doesn't understand that there's anything behind it, but the users, from their perspective, they understand it because something happens behind the scenes, something happens beforehand. And this is why we chose to use this cryptographical concept called multi-party computation. And when I first heard about multi-party computation, I thought someone was like kidding me, or it's like saying something that's a legend. It's impossible to, because the actual concept of multi-party computation is that me and other people, both called parties, we can compute something in a way that the entire computation is completely hidden, completely intact from both me and them. And only the resultant output is visible for both of us. And when you think about it from a computer science kind of philosophy, where you think of clients and servers, and you think of peer-to-peer, and you think about applications, and you think about inter-process communication, and you think, how am I supposed to run a computation that doesn't run here and doesn't run there, and no one can actually see what's going on in the computation, but on what CPU does it run, and what memory is accessed, but if it's on the memory, so how can I not read it? And you're like, I have no idea how that's possible. And it sounds like magic. And when it sounds like magic, it's often either bullshit or magic. And I think here it's actually magic. But when you actually look down, magic has this property that when you actually understand it, it's no longer magic. It's simply reality. It's simply equations. It's simply something that makes sense. But you need to dig very deep in order to understand that. And we use MPC in a very specific way. We use MPC just to make sure that both the user and the blockchain needs to participate in signing, but no party, no validator, no user, no one knows the private key that is used in order to sign a message. So they can compute the public key together. They know the public key. They know that together they have the private key, but no one tells the other party exactly what the private key is, because everyone keeps a part of the private key, like a share of the private key, hidden or secure in his own computer, right? And when you do something like that, then what you can actually guarantee is that both parties needs to participate in order to generate a signature, but the signature is matches this public key, which is just one address on every blockchain. So it's one address on Bitcoin, or one address on Ethereum, or one address, and you can later just broadcast this transaction into Bitcoin. You just take this output, put it on Bitcoin. Bitcoin sees a normal digital signature. He has no idea that MPC was used in order to generate it, and he simply accepts it and execute the transaction.
So I have to say that we are always fighting. This is our way to go through stuff. And you talked about the magic part of the MPC. And as part of that, it really sounds sometimes like those are things that are impossible to do, or sounds impossible when we try to break each other ideas. So can you give us some examples, like simple example of how it really works and how you can really break those ideas?
You mean a misuse
simple example of MPC or cryptography, and what are the mistakes that you can have?
Well, we keep making mistakes because we try to make things more optimized. So we try to innovate and cut things and reduce things. And well, in MPC there is this concept of rounds where the computation doesn't happen by me sending you a message and that's it. It's me sending you a message and you sending me a message and me sending you a message and you sending me a message. And that's frustrating because when you look at it, you're like, why do I need this? Like, you already have this channel, like I'm speaking to you already, like why do I need to first wait for your input and then answer another time? And it's like, it's frustrating. So you try to reduce the number of rounds, especially when it's revolving around a blockchain that throughput is very important and latency is very important. So you try to reduce everything. You try to always say, well, but this state-of-the-art article, is this really needed? Like, can I make it better? And one thing that we thought about, like first when I saw this concept of commitments, I saw this, one person sends a commitment into another person, which is just, I'm going in the future to tell you a value. I'm not telling you the value right now, but in the future, I'm going to tell you the value. And when I'll tell you the value, you'll know that I knew that value beforehand. And you think like, why do you need this? Why can't you just tell me the value now? Why do I need to first know that you know the value before you tell me the value? And there's a reason. Well, if you tell me a value and I tell you a value, then one of us needs to send a message first, right?
Right.
Because there's no like simultaneous, like it's impossible. Just networks. And if one of us sends the message first, it means that the other has an advantage. Because I can see your input, I can see your message before I tell you my message, which means that I can calculate something with your input, with your message, and then output something that is dependent of that input. And with that, I can do some nasty stuff. Like I can actually, there's some attacks that you can actually break everything like that. Well, for example, let's say that we do DKG, distributed key generation. Let's say that we just create a shared key between the two of us, right? That's the very basic thing in threshold signature, is that you create a private key that you have half and I have half, okay? Now let's say that you first say, this is the public key share of my private key, right? Because it's just a public key, like there's no problem saying a public key, right? And then I tell you what's my public key share, okay? But I see your input first. What I can do? Well, I can simply take your input and just put the minus there, right? And then together it comes out as 0, right? Now I have no idea what your private key is, but I know that together the private key is 0, right? And that's a problem, because now I can calculate signatures without knowing neither your or my share of the private key, just knowing the resultant equation, which is 0. And it doesn't have to be 0. It's just for an example. You can put any number over there, but basically that's how it is. And well, at first you said, yeah, but I would like to discard this. Like, what is this concept of commitment? Why do I need it? And then you discard it, and then someone will break your cryptography, and your entire solution, which you built over 2 years and raised who knows how much money and resources into supporting, is completely useless right now. So of course you cannot just do that stuff, and you wouldn't have been able to do it, because when you try to actually prove that this new scheme that you suggested is secure, then you couldn't have made the proof. Well, unless you're lying. But basically, this is the kind of thing that you can do when you try to optimize these things, or the kind of attacks that you have on cryptography that are very easy. But also the solution is easy. But if you look at commitments and you just say, I'm going to say something, and I say, I'm going to say something. Now, we both know that. And now it's safe for us to actually say that. And now we can validate that what you say now is what you were going to say. And with that, you don't leak any information about what you're going to say, but you assure that you had that knowledge beforehand. And well, I still think that there's ways to optimize these kind of things out, and maybe you'll have some surprises in the future. But for now, let's try to be very careful in what we try to reduce. It's not there for no reason.
So usually in engineering and computer science, when you build something, most of the work is on building it and proving that it's correct, right? And in cryptography, and this is a lot of what you were talking, this is also why we call it fighting, or we try to break it all the time, is that most of the work is not on building it, is actually trying to break it, right? So is that correct? Is that a good way to explain the work as a cryptographer?
If you ask Avichai, it's definitely the work of a cryptographer.
Yeah, Avichai is one of our cryptographers, one of the top cryptographers in Israel.
No, he just he has this thing, like he wants to break everything. We like to come up with solution. He like to break some, but it's good. It's this dynamic that actually helps us get forward. Yeah, it's a big part of our job as cryptographers, is to try and break whatever we do. But I think it's more intuitive design. Like you raise an idea and you want to judge whether it's something that's worth putting our efforts research-wise into it. And then before you actually try to prove it's correct, like that might take a lot of time. Then, well, first of all, you think like, does it even make sense? And the easiest way to show it doesn't make sense is to think for 5 minutes and understand if you can break it or not. And most of the time, the answer is that you can break it. And well, if the answer is that you can break it, especially if you can break it with a pen to pencil, like the Lev likes to do, then well, you can move on and just forget about this idea. But if actually you put some very concentrated thinking, you and the other team members think how you can break this thing. And well, the answer is that we have no idea how we can break this thing. Then your intuition changes, and maybe that's something that you can actually do and you can prove that it's correct. But I think, yeah, it's just one part of the process.
So what is really the process in cryptography? So let's say that I'm working on a new algorithm. At what point you feel comfortable with your algorithm that you can really use it in the real world? What do you need from that? What do you want from other people to help you with?
Well, I think for me, we have really gathered the top cryptographers. Like, I really have a dream team, and they have expertise both from theoretical and practical academy research, but they have also background from nation state level of cryptography and security. And this kind of makes it so that most of the ideas are just broken internally. And when they're not broken internally, when we are actually confident that this thing makes sense internally, then that's the first step. A step later is to actually formalize it, write it down, and try to prove it's correct. And after you did that, and you have this thing that you think that you have proven correctly, well, the scientific process calls for peer review. I think that's the level where you actually think something is secure. Well, at least the theory is secure after it's proven and then peer reviewed. But a proper peer review, like by people that you esteem and the academy esteem, and maybe you publish it in some convention or magazine that gives you that liberty or permission to think that it's actually made, actually secure. Then, well, the next step is to develop it or implement it, and that's the worst step, because most of the problems occur not in theory but in implementation. Well, there's a lot of attacks that you can make that are general, but there's also very specific attacks that you just, well, a developer sees an MPC paper and he sees all of these weird letters that he has no idea what kind of language is that, and one letter looks like the other letter and he has no idea what it means, and he just tries to implement it and he does something that is not exactly what the original authors suggested. For example, if you have this arrow left, it means that you need to uniformly sample in a random way from this group into that variable. It's like, yeah, of course that's what it means. Like, no, it doesn't mean anything for developers, and unless you're writing your own code as a cryptographer, which then, well, there's other consequences for that. Well, then you have to be very careful to work with the developer in choosing exactly what libraries for the math he will choose and how he will use it, and that he follows the process and the description of the algorithm very carefully, and that he has no other problem that he raised into the implementation. I think that's the key place where actually modern cryptography is broken today.
So the other part of cryptography is working with the developers and making sure that they're doing it correct, right? Correct.
Oh yeah.
That's a really, really good point. So let's get back to Odyssey and the wallets. So the whole idea of the wallets and Odyssey is to make those capabilities of being able to create a granular access control to access to other blockchains, very transparent for builders and users, so they don't have to think about, cryptography and MPC and security. You don't care about it as a builder or as a user. How much do you think it make it more complicated for the cryptographers and the developers to build Odyssey and to implement that because of this requirement?
Well, I think that we make the software design in a way that, like, the architecture is just designed in a way that these are completely separate modules. We try to do that. Well, of course, that the Odyssey developers will need to understand cryptography, but what I would like to do is that builders that build protocols on top of Odyssey, they wouldn't need to. That we abstract it away completely, that they will have something like, okay, do you approve this transaction or not? But they have no idea that actually, if they say yes, then some magic happens and the user and the blockchain together computes the signature. They just say yes or no. And on this side of the client end, and again, we would like to wrap the transaction, the communication with the blockchain as much as possible. I think that most times, well, users don't really need to understand that there's a blockchain in the backend. Why does it matter? A lot of times you can wrap it in such a way where, well, you have the security of the decentralization, but you don't have the user experience of blockchains today, that you don't need to have this asynchronous process and these weirdly formatted transactions. No, you just want a simple SDK that will tell you, create a new wallet or sign a message or change policy or something like that. Well, I want to make it as transparent as possible from both ends. In this regard, I don't think the cryptographers actually care about it. But what they would care about it is that I would come and ask them, yeah, but no, we can't do that. Like, yeah, I talked to this guy and he wants to do that, and for that he needs to know this. Well, can you make sure that he knows this? And it's like, this is hard. Like, this is really hard to prove. Yeah, but like, if you can prove that, then these new type of use cases can be built on top of our network. Like, for example, it's very helpful to have this access control layer just in regard of protecting your own wallets. It's already helpful. But then if you try to do something that is cross-chain, or you try to do something that involves knowledge about wallets or about prices or something like that, then you need some kind of decentralized, trustless oracles or input streams into the blockchain that will continue to prove or add state from other blockchains into our blockchain. And that's where we actually make a difference, I think, where we'll have a single place that holds information that is cryptographically proves secure about other blockchains, about the wallets that we have and their state of other blockchains and the state of the other blockchains, and the differences and prices and comparisons between these blockchains. Well, then a brand new world is opening.
So we have in crypto today not a lot of teams that working with modern cryptography. It's pretty rare, like MPC, but we have some. And Odyssey is doing something that is really different. So can you tell us, to the audience, to understand what is the real differences in terms of the modern cryptography and MPC to the most other projects that relies on MPC or other modern cryptography?
I think that the number one difference is that we are actually making a decentralized implementation of threshold security, but a completely decentralized implementation of threshold signatures. And not only we have it centralized in the way that the validators don't share all the information between each other, and you need to corrupt a certain threshold of the validators in order to corrupt the entire network or steal the secret of the network. We actually make the distinction that the user is always needed in the equation. And I think that together this is it truly difference. It's the true difference. When you're a user, you want to know that no matter what happens in the network, without your knowledge, the network cannot steal your money. And you also want to know that you need a catastrophic event in order for the network to actually not enforce the policy, the security policy. And that catastrophic event is something like 2/3 of the validators are completely corrupt, and either they've been hacked or they've been bribed or something like that. Well, that's very hard to implement. It's very hard to implement efficiently. It's also very hard to implement in general. And we also wanted to have this entire design in a way that the user has no idea about the state of the blockchain. Like you really want the user to feel like it's a normal blockchain, to feel like that's the entire thing that's going on there. So you want to have the entire blockchain as one virtual group, like one virtual entity, not as a list of players that communicate with you, because who knows what these players are going to be in the future, and why should I know as a user if I'm talking to 5 or 10 or 50 or 80, and who are they and what kind of IP addresses they are. And not only that introduces a completely new attack vector into the network, but it's also very awkward and very unnatural in how a blockchain is designed to be in the first place. Well, we want to do it in a way that the user has no idea. The user just chooses one transaction, one message to be signed. He broadcasts it into the network. And then in the network, some computation is done internally between the validators that he is completely unaware of. And then they compute a joint result, and the user can query it and understand that, well, this is the result I got from this virtual entity that's called the blockchain. Well, that's the way we think about it. We think about it as like MPC within MPC, right? You have the first layer of MPC, which is just 2 out of 2. And you have the second layer, which is T out of N inside of the blockchain. And I think that is something that no one has ever done before.
So what you're saying is that from one end, you need the user to participate in the MPC. The user must participate. But on the other end, you still have flexibility between the blockchain validators or not, right?
Yeah.
And this is the uniqueness, the real
Yeah.
uniqueness, and this is something that nobody does.
Yeah.
Perfect. So I think we can go to the last question, which will be more general question. If you can tell people that, into cryptography, what they need, what are, what the background, what they have to learn before getting into cryptography, and what it requires from your background, from your experience.
Well, it's kind of interesting because, well, first of all, we are doing this special training program. Well, we don't see this as a 5-month effort or a 1-year effort. We see this as a multi-year effort in completely changing the landscape of modern cryptography. And when you want to do something as revolutionary as we do, that goes even beyond what I've described in this video, well, you would need a lot of firepower, but that is very hard because there's only this limited number of quality cryptographers in the world, but there's a lot more talented and smart people in the world than there are cryptographers. And what we have started to do is take, like, for example, mathematicians and tell them, okay, you have this amount of months, you learn this amount of things in this amount of months, and then we test you and we see if you are, well, if you can participate in research. That's the only thing that I care about. Actually, we have already a student that has finished it, and he has some really great findings, and yeah, it seems like it really is working. And basically, besides reading a lot of either books or doing a lot of exercises and reading a lot of papers, I don't think there's anything completely special about it. What comes to mind when you say, well, what is special about being a cryptographer is, well, it's a body of knowledge that is very, very wide, and the intuition of a hacker, I think. Well, if you combine the both of them, if you have this wide body of knowledge, it allows you to do these associations. Well, it allows you to do new things that weren't done before, because you've seen it once, where in this article 10 years ago. Well, that's the kind of thing that you need experienced directors for the research for. But when you look at just this one particular research job inside this scope, well, then maybe you can do that after a few months of very hard training, and you can be directed toward that goal. And I think that's the kind of combination that we try to prosper here. Me and Dolev together, we are leading all the research done inside of the World Labs, and Dolev brings this wide body of knowledge inside of cryptography, and of course he has an amazing intuition, and I come from the cybersecurity proper, like, I've hacked this and this and this, and I defended against these kind of threats. And I think that together it's kind of a combination that is very, very widespread, very, very thorough. And well, with that, I think that there is an insane amount of talented people that can join effort in various ways and be directed, and maybe not that long from now can also lead the effort by themselves. That's, well, I have this belief that they can do it very fast.
Okay, thank you, Yehonatan, for chatting with me today about photography, or background, Odyssey, the wallets. It was really, really great to hear all of that. And people that are looking for, their challenge to be part of the future cryptography and the future of crypto, I think your team with Dolev is probably one of the top teams in cryptography.
I hope so.
And thank you, all of you, for joining us today. It was really great. See you on the next episode.
See ya.